idea that are on to to figure out so here we see virroa mite she turned, she jumps up, she jumps. As you look very closely, the mite comes around the back of that. So the bee starts grooming. So the bees started grooming, none of the bees were able to dislodge the parasite. So is this a common mechanism of mite transmission? Is it something that's happened in the history of bees and virroa mites? Maybe. But it absolutely shows us that we can't underestimate these parasites. They are able to do sophisticated things that we don't always notice. We just think of them as something to be poisoned or ignored, and we're just trying to focus on the bee biology instead. So, very, very uncommon, but these are our plausible mechanisms of natural mite spread. There's also non-natural mite spread. There's a lot of things that we do that can spread virroa mites between colonies. Moving brood, moving bees certainly are an easy way to take mites from one colony and put them in another. You could really move them with wood wire, things like that. But the most spread is that's something that we always in this colony. And so those mechanisms that we use in our cells can also spread parasites. So this is the takeaway of our virroa transmission section. Drift is happening can be mites, but it's mostly over short distance. It can happen over very long distances, and it can intensely transmit virroa. The better they are at transmitting, because the more guards they have to defend their country. And so in that paper, the published paper based on the graphs I showed, we decided that robber lure might be a better terminology than mite bomb, because a mite bomb blows up and shoots mite shrapnel at all the colonies nearby. That's not what's happening. It's the guilty parties here are the robber bees sneaking in and attacking down. It's just that it's been booby-trapped with virroa mites, and they're bringing those home, and that winds up making the robbing colony sick. We think the drift and robbing probably happen in natural settings like bees living out in forests, but we don't think that that's enough to completely eliminate this problem. Overall, though, this huge diversity of transmission mechanisms which means that under natural circumstances, we don't expect the bees or the mice to simply get nice with bees over time. So the strategy that we need to tackle is trying to keep our populations under control as we help to boost the resistance of the bees, because the mites are not going to be doing us any favors. When we think about transmission, think about those ideas of drift and robbing. This is here. It's important for us to think about when robbing occurs and when drift occurs. So my from just after golden harvest, the last bloom of the year, and for any additional sugar that they get. So that's when I have to be really mindful. You should be thinking about robbing and drift. Does drift happen? It happens whenever it's supply, but it's more likely to happen. It's more likely to happen when you eliminate any possible networks within your apiary. Coming back says, I'm not sure which one it is. I've got this mite on me, and it's really distracting. I'm full of these viruses, and full of nosema. All of these things are going to make that bee make more orientation mistakes. But if there were lawn flamingos in front of half the hives, and beach balls in front of the other, it's possible that the bees would be able to learn a little bit better which box to put into. If you want to keep your virroa mites low, and you should, you need to reduce the chances for drift and robbing. And the best way to reduce the mite-infested colonies nearby are to treat entire apiaries when a colony has very high mites. It's talking to your neighbors and figuring out what you're doing and what they're doing. Even if you're not in coordination, it's nice to know what's going on. And you need to think about wild bees or feral bees that might be living in trees or living in the walls of buildings, because they're not getting treated at all. They could be those perfect robber lures. They grow, they fill themselves up with honey, they fill themselves up with mites, they get sick, they die, and your bees go in and bring parasites home. Now, we've been talking a little bit in this section about treatment-free beekeeping. And so it's important, regardless of what your mite management strategy is, you're not a crummy neighbor. And so nobody would want to live next door to that. It's the kind of thing that makes you wish for a homeowners association, right? It's the only thing that makes you wish for a homeowners association. But if you are a beekeeper who is not keeping your varroa mites in check, you can try to reduce the impact on your neighbors by using robbing screens. If you prevent your bees from getting robbed out, that's better for your bees, and it's better for your neighbor's bees. If you are treating your bees, but your neighbor is not, if you think your neighbor is doing bad mite management, these don't cost very much. And it's a nice neighborly gift to say, hey, I don't want my bees to steal your hard-earned honey, so why don't you put these on all of your colonies so that my robbers will not be able to figure out how to get through. So it's a very, very cheap tool that you can use, whether you're the mite source or the mite recipient, to reduce the risk of that robbing-based mite transmission. So in that natural host species, in Apis cerana, the mites are typically going into just the drone brood, which are sacrificial anyway and can be removed when there's large numbers of mites in them. Drones are only reared briefly, so maybe the bees have actually adapted to do that. Apis cerana doesn't make drones year-round in large numbers. That's partially probably because they've been subjected to millions of years of varroa mite parasitism. Multiply infested drone cells get entombed, as we said, so that's a good way to keep the mite levels under control. And all of this makes them a sort of negligible pest. What we're looking at, though, if we think back to this, is an example where one of the species in the fight has fully elaborated itself. These are the varroa mites that have been on Apis cerana for millions of years. But the other member of the species is some dumb snake that was hoping to get half a bug, right? So what we wound up with here is our bees are fighting against not just an enemy, but a well-armed enemy that has been engaged in a tit-for-tat arms race with Apis cerana for a very, very long time. So we really need to hold our bees' hands and help them through this process, because we have introduced them to a parasite that nature had not introduced them to before. So in the remaining time, I want to talk just a little bit about selecting for varroa-resistant bees. There's a number of different mechanisms that you can use to try to produce a more mite-resistant bee. And there's different breeding programs that have focused on different traits. And so I'll talk about just a few of these traits here. These are different terms that you might hear. I'll show you each of them, so don't worry about skipping over this. But the important thing to understand is that there are selection programs all around the world. Individual queen breeders, some individual queen breeders in this room might be looking at some or maybe just one of these traits and trying to breed that into their bees. So it's important to understand what they are and understand the nomenclature. So one of them is the idea of hygienic bees. A hygienic bee is simply a bee that will detect that there's something wrong with brood, open the brood, and remove the brood and discard it. So a hygienic bee is typically evaluated using this, the freeze-killed brood assay, where you use liquid nitrogen to kill a circle of capped brood. You put that frozen circle, you let it thaw, then you put that circle of dead brood back into the colony, and you come back 24 hours later. And you simply ask, what percentage of those cells were the bees able to figure out that something had gone wrong, open them up, and rip those pupae out and discard them. So on the right, we can see a very hygienic colony that I subjected to this test. You pour the liquid nitrogen in. That's my little thermos full of liquid nitrogen that I used in the field. And this is a colony that passed that test. Another test you might hear about is varroa-sensitive hygiene. So again, it's the same hygienic behavior, finding brood that have issues, opening them up, and removing them. But in varroa-sensitive hygiene, you are specifically looking at sensitivity to the reproduction of varroa mites underneath those brood caps. So there's a lot of different tests. There have been more tests in the past, and people have started circling around them. One of the most common now is the Harbo assay, where you're simply doing this. You go into a colony, you figure out what percentage of their current young brood have varroa mites going in and trying to reproduce on them. You come back a little while later, and you go to that same frame, and you look at some older brood. That same group of bees, whose cousins or whoever, or sisters, you already have opened up to count mites in, you go back to again just before they emerge, and you figure out what percentage of those mites succeeded, what percentage of those mites were removed, and what percentage of those mites are still there having daughters. And by doing that test, we can get a VSH score and select for bees that have high VSH behavior. Another trait you might have heard about is grooming. This is totally different. It's not targeting the mites in the cells, it's targeting the mites as they ride around on the bees. And high grooming bees are bees that are going to be able to dislodge mites and do damage to them before they throw them down onto the bottom board. Because an undamaged mite who gets knocked off the bee is simply going to climb back up like that mite on the flower. So we use our screening bottom board, we look at these mites under a dissecting scope, we figure out which colonies have a whole bunch of mites falling that have damage to their legs, and then we breed from those colonies. And so this is an example of a video of some high mite bees. Sorry, some high grooming bees. So the first one wasn't very interested, but the second one was. She runs in, she grabs that mite. Now, unfortunately, because I'm a wet blanket, I will tell you that if you watch that video really closely, she doesn't kill that mite. She actually has that mite jump onto her face and then run over her head, just like I saw in that flower study. So it doesn't always work, but it does sometimes work. And so that's one trait. Another one that you might hear about is uncapping recapping, which is a behavior that we're just trying to learn more about now. But the idea is that essentially, instead of opening up every cell that smells funny and ripping the pupa out and throwing it away, maybe you're just going to open those cells up, you're going to pull out any brood that have problems, you're going to leave behind brood that seem okay, and maybe in that process, that male varroa mite, who's very sensitive, is going to get confused and wander out and get killed. And so this is a trait that doesn't require killing the brood, but it does still lead to negative consequences for the mites. So when you're sitting there and you're dissecting a whole bunch of brood caps, what you're looking for is a brood cap like this one on the right, brood cap F, where you can see that there's the shininess that you typically see on the inside of a brood cap is gone. That's from the cocoon that the bee spins as she's pupaing. But this little opaque, sort of matte surface represents a piece of wax that has been used to recap the cell that had been previously opened during the development of the brood. I will tell you, of all of these very tedious methods, this is the one I liked the least. Sitting there with my frame and my dissecting scope and my tweezers and my razor blades. But it is something that you can evaluate if you're so inclined. Perhaps the most interesting story, though, and the one that I'll end with, is examining this idea of survivor bees. So the Russian bees, the Russian bee breeding program, really ultimately arises from this idea that perhaps the bees that will do best against varroa are the ones that have already been subjected to them the longest. So the Russian queen breeding stock all came from Primorsky, Russia, which is just over here in eastern Russia, just north of the Korean Peninsula. So these are the varroa, or the honeybees that have been dealing with varroa for the longest. But there are other survivor bee populations that you can look at. The philosophy here is this. Maybe the best way to become better beekeepers is for us to understand how the bees would live without us, without our intervention, without us meddling, what would happen. And if we can figure that out, maybe we can use that to steer what we're actually engaged in. So this is a map that was published a few years ago of known survivor bee populations. And there's a bunch of them. There are some that were sort of fabricated from bees in Avignon, France, and in Gotland, Sweden. So these are both populations that were set up with varroa mites, and then they made some of them survive and continued tracking them. Primorsky, obviously, was just a population of bees that never got treatment. So they had to survive, or they would cease to exist. And one of these populations is the Arnott Forest in Ithaca, New York, which is convenient because I went to school at Cornell. And so this is the Arnott Forest. It's a nice place to spend your 20s. This is Tom Seeley, my PhD advisor and mentor. And this is the Tom Seeley that you might have seen giving beekeeping talks before. But to tell this story, we actually need to start with this Tom Seeley, high school student Tom Seeley, who's so fascinated by bees that he's spending the summer volunteering at the bee lab at Cornell, where his father is a horticulture professor. So Tom is at the bee lab, and he teams up with a student, and they go into the Arnott Forest, this forest owned by Cornell, in 1978, and they map all of the bee trees in the forest, just because they think that it would be a fun thing to do, and it was. They map all the bee trees, they figure out the density of bees. In 1995, varroa mites were found in Cornell's apiaries. So they showed up in the US in 1987. We got a few more years at Cornell, but eventually they did show up. And when they did, the devastation was real. It was very hard to keep those bees alive. And like any other population of forest-dwelling bees, Tom was sure that the Arnott bees had died. He was sad. They were bees he really liked, but he was sure that they had gone the way of so many other feral colonies. But he's a good scientist. So in 2002, he decided he would go to the forest and just confirm that there weren't any bees left. And there were bees. In fact, there were just as many bees in 2002 as there had been in 1978. It seemed like the population was basically doing the same thing. And everyone said, well, obviously that's because the varroa mites haven't gotten there. So he caught a bunch of colonies there. Where am I at? Here we go. So he caught a bunch of swarms and he tested them, and they did, in fact, all have varroa mites. So the mites were there. People said, well, yeah, sure, there are mites there, but they probably just arrived. So if you went back there 5 years later, they would surely all be dead by then. Well, in 2011, Tom went back, and there was the exact same density of colonies in the forest. So clearly something is happening here that is not easily explainable. So the mystery is, how are the Arnott forest bees persisting with varroa, but without any kind of varroa treatment? I'm going to jump ahead a little just so to make sure I have a lot of time. So a few mechanisms that we've considered here are possible mechanisms like hygienic behavior, higher levels of grooming behavior, that uncapping, recapping behavior, or maybe there's something about just living in a forest, a small nest size and really healthy living. You're far apart, there's less robbing, there's less opportunities for drift. Maybe that's what's keeping them alive. So this is me in grad school going out to a forest and setting up hanging swarm traps because there were a lot of bears. The bears ate a lot of my homework in grad school. But I was able to get a fair number of these Arnott colonies, and I was able to test them. Unfortunately, I don't have time to run through all of these graphs in detail, but I will essentially tell you that this is the pattern that we see. Let's see what happens if I do that. Can you hear me now?
Battery not dead.
Well, it's going to have to be a lot louder.
No batteries.
Can you hear me now? Yes. Okay. So, the short version of this is simply that if you look at the hygienic performance of Arnott forest bees, what we see is that the hygienic performance is okay. In one day, they're removing about 75 to 80% of the frozen brood. In 2 days, they're removing about 95%. That's pretty good. Actually, when Marla Spivak originally published on the hygienic test, they would have passed. It's because we so quickly selected bees that were so hygienic that she had to make the test harder so that not every colony passed. So that was what we wound up seeing with the Arnott forest bees, is that they were performing pretty well, but not fantastic. If you compare them to bees that we know are being selected for the hygienic test, they do worse. That's worse. I can only do so much. But if you compare them to unselected bees, like bees in our bee yard, or if you compare them to unselected bees from the 1990s, before any of the selection was taking place, either in Minnesota or in Australia, you see that my bees, the Arnott forest bees, are wildly outperforming the unselected population. So we can from this try to draw the inference that the Arnott forest bees are probably much more hygienic than their ancestors were, but they're not as hygienic as we can achieve with a really focused queen breeding program. If we jump to something else like grooming behavior, we see basically the exact same thing. So we can see on the left, the Arnott forest bees are grooming maybe 35% of the fallen mites. Commercial bees that are not selected for grooming, they're only grooming maybe 20%. In the Purdue experiment, when they produced the Purdue Aqualighter bees, the very first year they did it, they had about 5% of those mites falling through. But by the end of it, they were able to get up to about 50% of the mites falling through. So again, the Arnott forest bees are doing well, but they're not doing as well as a focused breeding program just on that one trait. The uncapping, recapping looks exactly the same. The Arnott forest bees have their level of uncapping, recapping. If you compare them, ignore the blue lines, just focus on the gray ones. These are other survivor populations around the world, and we can see that all of them are performing very similarly to the Arnott forest bees. They have mite-resistance traits. They actually have multiple mite-resistance traits. But if I took the Arnott forest bees and I put them into a hive, and I managed them for honey production, and I didn't treat them for mites, their mite population would grow, and they would die. are not mite-proof. Part of the benefit that they are able to get comes from the mite population growing continuously. The benefit to the mites is that over the course of a typical managed colony's lifespan, over the course of a year, the brood are continuously being reared, which means the mites can continuously reproduce. In a natural colony, you will often wind up with a brood break of some kind. As long as bees are reproducing, the mites can reproduce. If there's a break in bee reproduction, there's a break in mite reproduction. And that's going to make the mites more susceptible to being groomed, more susceptible to being caught out when they're trying to reproduce. So, if we look at experiments where we try to figure out how wild colonies live, this is what we see. The top line shows you, on top, that's a population of bees in large hives. Clearly it goes up over the course of the experiment. The population, the next line here is the population of bees in small hives. And so those small populations are not going to get as high. The graph below that is the mite population in those hives. And what we can see again is that top line is showing us the large colonies have a very dramatic increase in the mite population. The small colonies are keeping their mite population in check until all of a sudden they aren't. And that's because these were all done in the same apiary. And these small colonies went and started robbing the big colonies as the mites killed them, and then their mite population skyrocketed. We did this before we did my experiment, where we realized that we need to separate these sorts of experiments in the future. So the takeaway here is that if you have swarming, like you have in nature, or if you have small colonies that frequently get honeybound, like you have in nature, that's also contributing to their ability to suppress mite reproduction, to control the mite population. It's probably a combination of these different multiple mite-resistant traits in those R0 recipients, as well as their ability to suppress mite reproduction by having small colonies that swarm frequently, that have brood breaks, that are leading to this overall improvement in their ability to survive without treatment for virroa. I'm going to skip ahead. So the summary here is that these wild colonies are surviving because they have both good genes that give them behavioral immunity to mites, but they also have a good lifestyle, living out dispersed in the forest, swarming regularly, or being split if you're a beekeeper who's trying to simulate this. You can get some of these same results. Let's do this. There are dangers to being a treatment-free beekeeper who does not understand virroa. If you are a treatment-free beekeeper, you might be very well informed, you might have very good intentions, you might achieve very good results. You might also just be a crummy beekeeper who is lazy or ill-informed. And I can't judge whether you're one or the other, only you can. Or your neighbors can. But the important thing to take away from this is that you absolutely can be a treatment-free beekeeper, but it is your responsibility to know everything we've been talking about. You've got to be an expert on mite biology, bee biology, pathogen-host evolution, all the stuff we've been talking about. And you've either got to have no beekeeping neighbors nearby, or you've got to have an understanding with all of your beekeeping neighbors. Either they've got to be treatment-free too, or maybe you've got to be buying some robbing screens and passing them around. You've got to be able to assure them that what you are doing is going to lead to good overall outcomes. So if your mite management plan requires less work than just treating, then you're probably not doing it correct. Treatment-free beekeeping. Well, thank you.
Treatment-free, whoa, now I'm used to yelling. Treatment-free beekeeping is possible, but it is by far a harder strategy than just using chemical treatments as part of your mite control strategy. The last point I'll make here is that miticides, mite management techniques, things like drone comb trapping or other mechanisms where you're manipulating something about the hive without applying a chemical in order to kill the virroa mites, or using mite-resistant bees, partially mite-resistant bees, which is the best that I can realistically offer you, are all weapons in your mite control arsenal. You want to understand them. You can misuse them if you don't really understand the biology there, so you've really got to be a master of this stuff. And these different methods can actually work well or poorly together. You can wind up getting yourself in trouble if you've got a mite-resistant queen, and then you use formic acid to keep the mites down, and then you kill your queen. That might not be what you want to do. At the same time, you can synergize. You can do drone comb trapping, and then as you remove the trapped mites in the drone comb, maybe that's the time you do an oxalic acid dribble to just knock out the remaining mites in that colony. So there are tricks that you can use. We can't just wait for a silver bullet. We can't just try to find the one trick, the one strategy, the one bee that's going to solve our problems, because it won't. It hasn't yet, and I don't think it ever will. We're going to have to manage these together. Biology is always changing. These arms races are always going on, and we are now in the middle of one that we started by bringing these bees and mites together, and we're going to have to help our bees through the process. So, I'd like to thank the various funding sources that have supported this. I'd like to thank BetterBee, who's my sort of all-time funding source now, because they give me a full-time job. I'd like to thank virroa mites for giving me something to talk about. And I'd like to thank all of you for listening. So I don't think we have time for me to take questions, but,
We will take questions at the final panel session.
Good, perfect.
That's a perfect time to do that. Thank you so much. So just before people get up and move on, just another announcement. Only an hour and a half left to bid on this magnificent quilt. Raffle tickets, Dawn and Lisa, you know? Lisa's taking a break. Dawn is here. Raffle tickets, please. Also, after the event,